Welcome to AR Maths Pro Learning Academy. In this video, I'm going to explain relations and functions of Class 12 Mathematics, CBSE. Exercise 1.1 Introduction. Relations and functions. What is a relation? A relation is a connection between the elements of two sets. It is a connection between the two elements. For example, I have two sets, set A and set B. If there is a connection in between these two sets, that is called a relation. See, this is one connection. That's it. It is a relation. Furthermore, if we have two sets A and B, then the subset of the Cartesian product AB, A cross B, is a relation from A to B. Now, first of all, we try to explain what is a Cartesian product. Let us have an example. A set has two elements, 1 and 2, and set B has three elements, 3, 4, and 5. Okay. Now, what is a Cartesian product? Cartesian product is all possible ordered pair, which means all possible ordered pair means, try to understand, 1 with 3, 1 with 4, 1 with 5, okay, and 2 with 3, 2 with 4, 2 with 5. This is called a Cartesian product, all possible ordered pair. Now, let us define a relation in set builder form, which is equal to this: xy such that x plus y must be less than or equal 5 for all x belongs to A. X belongs to A means set A, and y belongs to B means set B. Okay. Now, if you see this one from the Cartesian product, the condition says for the relation x plus y must be less than or equal to 5. So, in this relation, we are going to take 1, 3, because 1 plus 3 is 4. So, it is in our relation. 1 plus 4 equal 5. It is in our relation. 1 plus 5 equals 6. This is not in our relation. 2 plus 3, 5, yes. 2 plus 4, 6, no. 2 plus 5, 7, no. So, the relation has 1, 3, 1, 4, 1, 2, 3. Now, in this relation, I have only 3 connections, which is a subset of the Cartesian product. That is why any relation is going to be the subset of the Cartesian product. Now, how many relations I can make it by using these two sets, set A and set B? This is one more question. Try to understand how many relations I can make it, which is nothing but 2 to the power of number of elements in A times number of elements in B. So how many number of elements here in A? I have 2, okay, and number of elements in set B is 3. So I will write 2 to the power of 2 times 3, which is 2 to the power of 6. 2 to the power of 6 means 64. So we can make 64 relations based on these two sets. Anyhow, conclusion is a relation is a general connection between two sets. That's all. Now, we'll talk about functions. Okay, we'll talk about function. A function is a special type of relation. Special type is nothing but a condition. That's it, a rule. In a function, every element of set A, which means domain, is related to exactly one element of set B. Okay. Now try to understand. Let us have an example. Then you will get understand. Now set A has 3 elements, 1, 2, 3, and set B has 3 elements, A, B, C. Now there is only one connection with each element of set A. It cannot have 2 elements. if it has two connections, which means it is not a function. It is not a function. So functions is going to be related with exactly one element with the set B. If any element of set A maps two or more elements, two or more, try to understand, two or more, then it is not a function. Anyhow, in general conclusion, function relation with a rule. Each input has exactly one output. That's all. Based on functions. Is this a function or not? Okay. First of all, it is a relation or not? Yes, it is a relation. Okay. As well as it is also a function. Okay. Now see here another example. Is it a relation? Yes, it is a relation. As well as it is a function. Now in this example, try to understand. Two elements has one output. It can be, but check, one element doesn't have two outputs. That is why this is a relation as well as a function. Example number 3. Is this a relation? Yes, it is a relation, but it is not a function. It is not a function because element set A element 1 has two outputs, and the function definition says it has only one output, exactly one output, not more than one. That is why it is not a function. Another example, see, is this a function? Sorry, first of all, relation. Yes, it is a relation. Is it a function? No, it is not a function because every element of set A must have an output. Okay, but here element 4 of set A does not have any output, so that is why it is not a function. Every function is a relation, but every relation is not a function. What is an empty relation now? An empty relation has no pairs at all. No pairs at all. Let us have an example. Set A has 2 elements and set B has 3 elements. And this is Cartesian product. We know it quite well. Okay. Now I'm going to define a relation such that x plus y must be greater than or equal 10. Now from the Cartesian product we need to check, okay, whether it is in the relation or not. 1 plus 3, 4, less than 5. 1 plus 4, 5, no, less than 5. 1 plus 5, 6, less than 10. 2 plus 3, 6. 2 plus 3, 5, which is less than 10. 2 plus 4, 6, which is less than 10. 2 plus 5, 7, which is less than 10. So in this relation, I do not have any connections. That is why it is called an empty relation, which is also a subset of the Cartesian product. Remember this one. The next one, universal relation. A universal relation is a relation in which every element of set A is related with every element of set B, like a Cartesian product. But Cartesian product is a set, okay? Universal relation is a relation, okay? That is the difference between these two things. Let us have an example. A set A has 3 elements and set B has 2 elements. We know the Cartesian product, all possible ordered pair. Now let us define a relation x plus y such that x plus y must be less than or equal 8 for all x belongs to A and y belongs to B. Now check from the Cartesian product. 1 plus 4, 5, which is less than 8. 1 plus 5, 6, less than 8. 2 plus 4, 6, less than 8. 2 plus 5, 7, less than 8. 3 plus 4, 7, less than 8. 3 plus 5, 8, which is equal 8. So all are under this relation. So such relations are called universal relation. A relation contains all possible ordered pair, as like Cartesian product. But this is a relation, universal relation, but Cartesian product is a set. Try to keep it in your mind. Okay, the next one. What is a trivial relation? A trivial relation on a set A is one of the two extreme cases of relations. What are those? The first one is an empty relation, and the second one is called universal relation. These two relations are called trivial relation. So the word trivial refers to either empty relation or a universal relation. The next, identity relation. The identity relation is the relation where every element of set A is related to itself only, related or connected to itself only. For example, I have a set A, comma A. All A belongs to A. Let us have an example. A set A has 3 elements, 1, 2, 3, and they are connected with themselves. See, element 1, which is of set A, is connected to 1, 2 with 2, 3 with 3, which is called an identity relation. This is an identity relation. Keep remember, he said identity relation is a relation where every element has connected with itself only. Then only it is an identity relation. Example: a relation R on A, R equal 1, 1, 2, 2. Is this an identity relation? No, it is not an identity relation. Why? Because in this relation 3, 3 does not belongs to the relation R. That is why this relation is not an identity relation. Reflexive relation. A reflexive relation on a set A is a relation in which every element of set A must be connected with itself. This is an obligatory part. But reflexive relation may also includes other pairs in addition to the self-related pairs. Let us define a relation. Let us define a set, and then in that set we will talk about what is a reflexive relation. Let us have an example. A set A has 3 elements, 1, 2, 3, and a relation R B on set A. Okay, so this is mandatory part to itself, connected with itself. Okay, but it may also have pairs like this. So a relation R equal, this part is obligatory. That is why he said every element of set A must be related to itself. This part is obligatory. Obligatory means it is must. But the rest of the part, this part, the other connections are optional. It could be, it could not be. Okay. For example, let us see an example. So it is a reflexive relation. Now, another example. Now check whether this relation is reflexive or not. Check ordered pair with same elements must be there. Yes, it is there. 1, 1, 2, 2, but 3, 3 is not there. 3, 3 is not there. That is why this is not a reflexive relation, as 3, 3 does not belongs to the relation. I hope this example is clear. Another example. See here, a relation on set A. ordered pair with the same elements must be there. 1 1, 2 2, 3 3. This is an obligatory part. It is must. The other relations, the other connections, the other ordered pair are optional. It could be, it could not be. So it is a reflexive relation but not an identity relation, because identity relation you will have only this part. That is why I wrote but not an identity relation. Now note, a reflexive relation on set A may or may not be an identity, but all identity relation set on set A will be always reflexive. Now, what is a symmetric relation? A relation on set A is called symmetric for all A comma B belongs to A. If A B belongs to R, then it must be B comma A belongs to R. Then only it is a relation. Then only it is called a symmetric relation. If one element is related to another, then the second element is automatically related to the first one. If it is not, then it is not a symmetric relation. Let us have an example. A set A has 3 elements, 1 2 3. A relation on set A R equal 1 comma 1. Check. All ordered pair with the same elements are satisfies with the symmetric condition. It is under symmetric condition. Now 1 3 is there, and 3 1 is also there. Then this relation is a symmetric relation. If A comma B belongs to R, then B comma A must be belongs to R. Then it is a symmetric relation. Let us have another example. Another example defined as R equal 1 comma 1, 2 comma 2, and 3 comma 3. Check. All ordered pair with the same elements are satisfied with the symmetric relation. So all satisfies with the symmetric relation. As A comma B belongs to R, then B comma A belongs to R. So it is also a symmetric relation. Now see the third example. A relation R equal 1 3 is there, and 3 1 is also there. So these two ordered pair satisfies the symmetric relation. But 2 1 is there, but 1 2 is missing. As here A comma B belongs to R, but here B comma A doesn't belongs to R. That is why it is not a symmetric relation, as 1 comma 2 does not belongs to the relation. So it is not a symmetric relation. Transitive relation. A transitive relation on set A is called transitive for all A comma B comma C belongs to R. If A B belongs to R and B C belongs to R, then it is must be A C must be there. Check. A B, B C, and A C must be there. This part is mandatory. If I don't find this part in the relation, then it is not a transitive relation. If an element is related to a second one, if the first element is related to the second one, and second one is related to the third one, then the first must be related to the third one. The third part is mandatory, Shabab. Now, let us have an example. I have a set A, B, C. Then a relation R equal 1 comma 2, A comma B and B comma C and AC. A, B and B, C and AC. So it is a transitive relation. Few more examples. Another relation R on A. A, B is there. B, C is there. But AC is not there. AC is missing. So it is not a transitive relation, as AC does not belongs to R. That is why this is not a transitive relation. One more example. Note, if note, this is very important note. Try to understand. AB belongs to R and BC is not there. AB is there in the relation, but BC is not there, then it is not required to check. It is not required to check AC. I don't need to check AC. AB is there, BC is not there. So that this AB satisfies transitive relation. So AB is there, BC is not there, then I don't need to check AC. I'll give you an example, you will get the idea. See, a set A has three elements, 1, A, B, C. Now, I define a relation, AB is there, but BC is not there. So I don't need to check AC. I don't need to check AC. It is a transitive relation. That's it. It is a transitive relation as BC is not belongs to R. So it is not required to check AC. I don't need to check. It is a transitive relation. Few more examples so get more idea. Now see here. Every ordered pair of the form A comma A is a transitive relation, which means ordered pair with the same elements, it is satisfies with a transitive relation. Now example 3, okay, I have a set A which has three elements A, B, C. Now a relation R on set A is AB is there, BC is not there, so I don't need to check AC. So this AB satisfies with the transitive relation. Now, ordered pair with the same elements satisfies the transitive relation. So this relation R is a transitive relation. It is a transitive relation as BC does not belong to R, so I don't need to require to check AC. Moreover, I know all ordered pair with the same elements satisfies the transitivity condition. So this relation is a transitive relation. Let us have few examples based on transitive relation. We have a set A 1, 2, 3, three elements and a relation R on set A. So we need to check this relation is a transitive relation or not. So we have to check each ordered pair. 1, 2 is there. Let us have cases. 1, 2 is there. 2, 3 is also there. 1, 2 is there. 2, 3 is also there. Then it is must. 1, 3 must be there. 1, 3 must be there. Yes, it is there. 1, 3 is there. So this satisfies with this ordered pair satisfies the transitive relation. Now check the second one. 2, 3 is there. 2, 3 is there. And 3, 1 is also there. 2, 3 and 3, 1 is also there. 2, 3 and 3, 1 is also there. So it must have 2, 1. In the ordered pair, 2, 1 must be there. But I don't find 2, 1. So 2, 1 does not belongs to the given relation. So the given relation R is not a transitive relation since 2, 1 is not belongs to R. Let us have another example. Set A has three elements 1, 2, 3 and relation R be on set A. Now we need to check this relation R satisfies the transitive condition or not. As we know that all ordered pair with the same elements satisfies the transitive condition. So I don't need to check 1, 1. Now 1, 2. So in this one we have three same 1, 2, 2, 1 and then 1, 2, 2, 2 and then 1, 2, 2, 3. So I have to check one by one. So that's why I'm writing in case 1. 1, 2 is there and 2, 1 is also there. 1, 2 is there, 2, 1 is also there. So 1, 1 must be there. Yes, 1, 1 is here. In my relation, 1, 1 is there. So this one is satisfies. Now the first with the second ordered pair with the fourth one. Okay, 1, 2 and 2, 1. 1, 2 and 2, 1. Sorry, 2, 2. 1, 2 and 2, 2. So 1, 2 must be there. 1 2 must be there. Yes, it is here. Okay, the second case is 1 2 2 1, and then 1 2 is also there. So this is also satisfies the transitive condition. The third part, 1 2 and 2 3. The third case is 1 2 and 2 3. So if 1 2 is there, 2 3 is there, so it must be 1 3 must be there in my relation. 1 3 is there? No, 1 3 is missing. So 1 3 is not in my relation. If 1 3 is not in my relation, then the given relation is not a transitive relation. Since we can write it, if AB belongs to R and BC belongs to R, then AC must be belongs to R. That is the condition of transitive relation. That is why it is not a transitive relation. Let us have few more examples based on this one, because this topic is a bit difficult. Now, set A has 1 2 3 elements, and R be defined, relation R be defined as 1 2 and 1 3. Check, 1 2 is there and 2 3 is not there, so I don't need to check 1 3. 1 2 is there but 2 3 is not there, so I don't need to check 1 3. So this satisfies the transitive condition. The second part, 1 3 is there, 1 3 is there, okay, and I don't have 3 2, but we don't have 3 2. So I don't need to check the other ordered pair 1 2. So this is also satisfied the transitive condition. So both ordered pair satisfies the transitive condition. So the given relation R is a transitive relation. Is a transitive relation. Now, equivalence relation. What is an equivalence relation? Equivalence relation is nothing but a relation which satisfies reflexive, symmetric, and transitive. All the three relations satisfies, then it is a transitive relation. All identity and universal relations are always equivalence relation, which means all identity relations and universal relations are reflexive, symmetric, and transitive. Let us have some practice work. Okay, you do this practice and write the answers in the comments below. Okay, so these questions are practice. You just need to put a check mark if it is reflexive, transitive, or symmetric. Okay, just make a note and try to solve it. I will give you the answer key in my next video. So if you learned something new today, hit the like button, share with your friends and family, and don't forget to subscribe. Thank you so much.